So, hi everybody for the seventh session of What Geochemistry Tells Us. So, our first presenter for this session is Alessandro Aiuppa from the University of Palermo on carbon dioxide flux emissions. So, Sandro, it's all yours.
Thank you, Arthur. Thank you for your kind invitation, and thank you for inviting me to talk about carbon and carbon dioxide emissions from volcanoes, my favorite subject. And I wish to start by saying this is not my own work, but the work of a great big team of people that includes the board of directors of the DECADE project, a group of friends from Italy, and a group of volcano observatories from many places around the world. And it's thanks to them that these results have been possible. So a brief outline, I will first describe the motivation that led us to think to a new research project called DECADE, a sub-project of the Deep Carbon Observatory. Then I will describe the state of the art of the topic of carbon dioxide emissions as the project started. And then I will try to summarize the actions we made during the project to try and go behind the state of the art by presenting results of CO2 emissions from different kinds of emitters, strong volcanic emitters, strong volcanoes on our planet, the weak volcanic gas sources, volcanoes under eruption, diffuse degassing. And then by summing up these four forms of carbon dioxide emission, I will try to synthesize and end up with a final estimate of the CO2 output from subaerial volcanism. And finally, we'll make some brief discussion on tectonic degassing and end up with some conclusions. But I would like to start by saying why carbon, why studying carbon emissions from volcanoes is so important. And I'd like you to concentrate on the bottom plot that is showing the evolution of CO2 concentrations in the Earth's atmosphere over the Phanerozoic, so over the last 400 million years. So we are basically here. This is where we are at the moment. And so to the right, the future projections of how the atmosphere will behave in the future. And to the left, the geological past, so a record of CO2 concentration in the geological atmosphere of our planet. And the key message in this plot is that each time the atmosphere has been reaching carbon, the Earth has warmed up. As you can see, there is a clear correspondence between peak in the CO2 record and peak in temperature in our country. So the point is even more clear if we focus on the Cenozoic, so the last 65 million of years of geological history of our planet. And again, as you can see, when the composition of the atmosphere is low in carbon dioxide, then the temperature is low, while when CO2 is high in the atmosphere, the Earth warms up. So it is clear that there is an atmospheric carbon control on climate. If you increase carbon in the atmosphere, then the Earth will become warmer and warmer. So it is important to understand what is driving, what is controlling the carbon concentration in the atmosphere. And this is the so-called geological carbon cycle, in which carbon is essentially released by volcanoes entering the Earth's atmosphere, from which it is removed via rainwater, then entering the hydrogeological cycle to be transported by rivers into the ocean, where it is used by organisms to produce shells and therefore to be deposited as limestones and carbonates that are finally subducted back into the mantle via subduction. So this is the kind of processes that are controlling the CO2 concentration in the atmosphere. The problem is that we know this cycle in a very bad way. There are very large uncertainties on both reservoir and fluxes. I'd like you to pay attention on this diagram just on the orders of magnitude, not on the real numbers. So in red, you see a reservoir, so the amount of carbon contained in the mantle, in the Earth's nucleus, and so on. While in blue, you can see the fluxes, so how carbon is transferred from the Earth's interior toward the atmosphere. An important fact is that there are wide ranges, large uncertainties into these numbers. And this is mostly because measuring carbon dioxide from volcanoes is very difficult. So volcanoes are the most significant natural source of carbon to the atmosphere, but measuring this emission has traditionally been very challenging. And this is because the atmosphere is already full of carbon, and it is very difficult to resolve the volcanic injection into the atmosphere from the atmospheric background. So measuring carbon has been impossible so far in a direct way. So we have to measure carbon dioxide indirectly. So what we typically do is that we measure the sulfur dioxide flux, which is possible thanks to UV spectroscopy with instrument called the COSPEC, the DOAS, or any other instrument looking at volcanic plume in the UV region. So you can easily measure the sulfur dioxide flux, and then you can measure the composition of the fumaroles, of the gas, either because you sample the fumarole or because you can use instrument in real time to measure the composition of the gas. And if you measure the composition, if you have knowledge of the carbon to sulfur ratio in the gas phase, then you can multiply the two and derive the carbon dioxide flux as a calculation. And the problem is all these kind of operations are difficult, challenging, risky for operators, and therefore it takes taken more than 40 years before we have been able to accumulate sufficient data to obtain a robust estimate of carbon dioxide emissions from volcanoes. And this plot here is offering a sort of historical record. So it is showing how estimate of the CO2 flux from volcanoes have varied over the years. And as you can see, there have been a number of estimates over the years, and the range is so huge. So estimates range from a few tenths of teragrams of carbon dioxide being released every year up to several hundred. So what is true? What is the real CO2 flux emission from volcanoes? And in order to try and answer this question and many other questions, the Deep Carbon Observatory was launched. That was a huge program, a 10-year program funded by the Sloan Foundation in the US at $15 million US. And the program involved more than 1,000 scientists from 55 countries. And our specific role in this project was to run DECADE, which was a sub-project of the Deep Carbon Observatory. This project started thanks to the initiative of the late Eric Cowrie, and the ambition of the project was to improve our estimates of the global carbon emissions from volcanoes. So this slide summarizes the states of the art at the onset of the project. When the project started, about 10 years ago now, we only had CO2 flux data for a very limited number of volcanoes, only 33 volcanoes. Take in mind that there are hundreds of volcanoes degassing on Earth, which means that if you want to end up with a robust calculation of the global CO2 flux, you need to extrapolate what is known, 33 volcanoes to the unknown, and this is very complicated. In addition, data at that time had been, even at the 33 volcanoes, very discontinuous, sporadic, and they were concentrated in a small number of volcanoes in developed country, while we completely missed CO2 flux information for key regions of the globe, such as Vanuatu, Papua New Guinea, Southern America, Indonesia, and so on. So I would say our understanding of carbon emissions from volcanoes was very preliminary at the time. And this is why the project started, and there were two kinds of key actions that were performed during the project. One was to establish a global network of instruments through which we were able to measure in real time and in the long term volcanic gas emissions from a number of key volcanoes. You can see them in the map. And the second main action was to found, promote, develop a number of field campaigns on volcanoes that had never been measured for carbon before. And this intense survey activity allow us to increase the number of volcanoes for which CO2 flux data are available for only 33 at the beginning of the last decade to more than 100 today, which allow us to refine our inventory. This also included a number of strange campaigns in which we were able to fly a drone from several kilometers downwind the volcano to fly inside a dense plume, say hello to the magma as it was degassing, and get good information on the composition of the gas on otherwise remote and inaccessible volcanoes. I'm going to then try to summarize our results, and in order to do so, I'm going to distinguish volcanoes in two big categories: strong volcanic gas emitter and weak volcanic gas emitter. Strong volcanic gas emitter are by definition the strongest volcanoes, those volcanoes in which you can go and you can clearly see the plume releasing a lot of sulfur dioxide in the atmosphere. You can see by hives, you can see with a spectrometer from ground, but since the emissions are so important, you can also smell this gas from space using satellites. And satellites have been key to studying these volcanoes because using satellites, you can have a coincident, simultaneous view of all the volcanoes globally that are releasing gas in a substantial way. And for instance, here I'm showing the case of the Aleutian and the case of Indonesia as just two cases. And you can see the most degassing volcanoes as red dots in these maps. So Simon Carr in 2017 ended up with this seminal work in which he was able to identify the 91 strongest degassing volcanoes on Earth. He was able to rank those volcanoes from the strongest to the less intensively degassing, and he was able by summation to quantify the total sulfur dioxide emission from these volcanoes at 23 teragram per year on a decade average basis. So we have very robust understanding of sulfur dioxide emissions. So in principle, if we add the information on the carbon to sulfur signature of these volcanoes, we could multiply this by the SO2 flux to quantify the CO2 flux very easily. The problem is that many of these volcanoes are very difficult to access. They are located in poorly inhabited regions, in very remote regions. So at the time of Carr work, only 40 out of 91 volcanoes had composition information available. The situation has improved with DECADE, of course, and we now have 57 out of 91 out of the 91 strongest volcanoes degassing on Earth with contemporaneous compositional and SO2 flux information. So for these 57 volcanoes, you can easily convert the SO2 flux in the CO2 flux because you do have compositional information available. The problem is what to do for the remaining volcanoes for which we don't have any compositional information. And this is why we played a lot in the project trying to find out new strategies, new approaches to extrapolate volcanic gas catalogs to account for the CO2 flux contribution from volcanoes that are unmeasured since so far. And we came up with the ideas of using rocks instead. Why rocks? I think this map explains the point easily. This map taken from the Earthframe compilation is showing our current database of volcanic rock compositions worldwide. And as you can see from the map, we have a lot of information on volcanic rock composition, much more than we do know for gases. So in principle, rocks are very well known, and if we could establish a relationship between rock composition and gas composition, then we could use this relationship to infer the gas composition at unmeasured volcanoes. And this is in fact what we did. The idea started from work we have been doing in Central America. Central America is an ideal laboratory because it is an area where rock and gas composition vary a lot along the arc, basically in response to variation in subduction properties, morphologies, and so on. Especially, we know that in Central America, in Nicaragua, we have a lot of slab fluids contributing to magmas. We know this because the magmas are very rich in barium, very rich in uranium, very rich in elements that are delivered by the slab, and it is entering the mountain ridge. While further north in Guatemala and south in Costa Rica, we have much less contribution of slab fluids as informed by lower barium, uranium concentration. So we have a range of slab fluid contribution to the magma. And the important thing is that if you plot the composition of the rocks against the composition of the gas for the same volcanoes, then you clearly see a very nice correlation between the two. And this correlation is not unique to Central America, but we have been able to establish similar correlation in other sectors, such as Southern America, such as the Sanda-Banda arc in Indonesia, and so on. So the key message is that arc gases and trace elements in volcanic arc rocks are regionally and globally linked. The second important point is that if you take the mantle weight, the depleted Moore mantle, as a reference, then arc gases are enriched in carbon relative to that, and this level of carbon enrichment scales well, is very well correlated with the level of enrichment in lithophile elements coming from the slab. So we have a global association between rock and gases that we can now use for extrapolation purposes. And to show you what we did, I'm making the Southern America example. So if you study Southern America, you know that you have an increasing contribution of slab fluid from south to north. So the slab is contributing more carbon, more barium, more uranium as you move from south to north along the arc. And importantly, you have rock compositional data available throughout the entire arc. But you miss gas information for Ecuador. We are ignorant on what the gas composition for Ecuador could be. So what you can do is draw a regression line through the gas rock correlation plot, and then use the composition of the rocks and this regression line to infer, to calculate, to quantify what the gas composition, volcanic gas composition should be for Ecuadorian volcanoes. Then, of course, you can climb those volcanoes, you can measure the composition, and you can compare the measurement with your prediction to find that they do match very well. Of course, we have been doing this calibration and these tests in many other volcanoes, and they worked. So we have found a way to extrapolate the incomplete volcanic gas catalogs by using the very complete rock catalogs. And so by combining the CO2 flux record with measured or extrapolated carbon to sulfur ratio data, we have been able to quantify CO2 emissions for all the 91 strongest volcanoes on our planet. And we estimate that these 91 volcanoes release between 36 and 39 teragrams of carbon dioxide every year. You can see that volcanoes in Congo are the strongest emitters of carbon on Earth, followed by a volcano in Mexico, then Etna in my own country, and then so on. We have also found very interesting geographical relationship between the level of CO2 emissions and the position of each volcano. So in this map here, I'm showing the location of the 91 volcanoes, and the size of the symbol is proportional to the carbon dioxide flux emission. So bigger symbols, it means larger carbon dioxide emissions. And as you can see, all the strongest volcanoes are centered in equatorial regions where sediments that are submitted underneath volcanic earth are richer in carbon because of higher oceanic productivity. On the other hand, where sediments that are subducted are low in carbon, as for instance between Japan and Alaska in this area, these low carbon sediments reflect in low CO2 flux emissions from volcanoes. So there is a global link between what is being subducted underneath the volcano and the amount of carbon that volcano will be releasing through volcanic gases. Okay, so this is what we know for strong volcanic gas emitters. But of course, we also have weak volcanic gas emitters. What do I intend with weak? Weak volcanic gas emitters are volcanoes that are dormant, that are quiescent, that are not erupting regularly, and in which you can go and you don't see any plume at all. Or you can go to Solfatara and you just see small fumaroles, but you don't see a plume. So you might be tempted to think that these weakly degassing volcanoes are not releasing carbon dioxide, but you would be in error because such volcanoes are strong carbon emitters, even though they don't have a visible plume. Fact is that the majority of holocenic volcanoes fall in this category. Of the 900 holocenic volcanoes, we can count more than 700 holocenic volcanoes that are only weakly degassing. But unfortunately, we only have data for 19. So if you are young and if you want to do research, this is an open research topic, try and identify new ways to measure carbon emissions at volcanoes that do not have a visible plume. Anyway, using those 19 volcanoes, we were able to make some calculation and extrapolate and quantify that there must exist on our planet more than 300 volcanoes that are weakly degassing, and that in total are releasing 15 teragrams of carbon per year, which summed to the 39 teragrams of carbon released by strong volcanic emitters, quantify the total carbon emission from passive degassing, from volcanoes not erupting at slightly more than 50 teragrams of carbon dioxide per year. Okay, this also only takes into account passive degassing, quiescent degassing, no eruptions. But we know very well that volcanoes are also erupting. And here I'm showing Mount St. Helens in 1980 or Pinatubo in 1991. Or if you want something more recent, you can concentrate on Soufrière. There is now erupting very vigorously. And of course, releasing carbon and sulfur to the atmosphere as seen by satellites. So we need to be able to also quantify carbon dioxide emissions from erupting volcanoes And it is something we did, again, using CO2 emission detected from the space, multiplied by carbon to sulfur ratios in eruptive plumes or in gases taken close to eruptions. And by multiplication, we were able to quantify carbon dioxide emissions from volcanoes under eruptions. And as you can see, this number is not very accurate, but it's very, very low. I told you before that passive degassing contributes around 50 teragrams of carbon per year, and this is only 1.8, just reminding us that eruptions are spectacular, they are beautiful, they are frightening, but at the very end, they do produce a very small fraction of the global carbon budget released from volcanoes. And finally, we do have a fourth type of carbon dioxide emission, which is diffuse degassing, which is very difficult to quantify because it is something we don't see. Diffuse degassing is the silent, invisible release of carbon through soil and through flanks of volcanoes. We might be tempted to think diffuse degassing is not that important, but in fact, especially at dormant and calderas, dormant volcanoes and caldera is perhaps the most significant form of carbon dioxide emissions from volcanoes, and sometimes can also create spectacular phenomena such as healing forests in the absence of an erupting volcano. In DECADE, we have been doing a lot of work to also trying to quantify this diffuse gas contribution to the global carbon budget. And what we know is that these diffuse emissions must be very important. Just to make an example, here in the left diagram, I'm comparing the emissions, the carbon emissions from Stromboli in orange, a persistently erupting volcano in Sicily, against Campiflagray, in which there is no plume, there are only very weak fumaroles, but the soils, the flanks of this caldera are releasing, on average, much more gas in a silent mode than an erupting volcano like Stromboli. By using existing catalog of diffuse gas emissions, we were able to indicate that diffuse gassing globally must account between 80 and 90 teragrams of carbon every year, which is even more than what erupting and quiescent volcanism is actually releasing. And so, to conclude, this is where we came up with the project. Our most recent estimate are estimate 19 and 20, and they've been obtained thanks to this DECADE project. And according to our refined estimate, volcanoes, and especially subaerial volcanoes, is releasing every year between 144 and 171 teragrams of carbon every year, with more than half, here shown in yellow, released by diffuse degassing. I'd like to point out, however, that what I've shown is only part of the game. And in fact, I'm here discussing only volcanic degassing. Gas is being released in diffused or concentrated form from volcanoes. But we do know that a large amount of carbon is also released away from volcanoes. Because if you move in seismically active regions, in regions where active tectonics exists, then as this map shows, then you do find CO2-rich springs and CO2-rich soil, such as in the Eastern Africa Rift, such as in Himalaya, and such as in central Italy. So you have huge amount of carbon being released even without volcanoes, and this is what we call tectonic CO2 degassing. And perhaps the best place on Earth where this process is being studied is in central Italy, but I wish to point out that this huge number refers to only a very small fraction of Italy. So considering that the entire Mediterranean area is infested by this CO2 degassing problem, one may wonder how big is the CO2 flux emission from the Mediterranean and globally in terms of tectonic degassing. And to my knowledge, there is only one estimate that has been foreseen so far, again from the DECADE project, trying to quantify this tectonic CO2 flux on a global scale. And according to this global study, tectonic degassing is releasing about 0.3, 0.4 gigatons of carbon dioxide every year. So way more what is released by volcanoes. So the message is volcanoes are important, but tectonic degassing, non-volcanic degassing globally could be even more substantial than volcanic degassing. Bad news, however, if we combine volcanic and tectonic degassing together, we obtain this number here, which is trivial. It's negligible compared to the amount of carbon dioxide that human beings, human activities are releasing every year since the Industrial Revolution. So bad news is that the future is not a good one because human beings are releasing much more carbon, two orders of magnitude more carbon than volcanic activity is releasing every year through volcanic and tectonic degassing. One may wonder why then, in the past, in the geological past, CO2 concentrations have been much higher than today, like in the Mesozoic or in the early Cenozoic. And the fact is that volcanism and seismicity and tectonism was much more important in the geological past. Here I'm showing global maps of our planet at time zero, so today, and in the geological past, to show that in geological past, for instance, in the Mesozoic, volcanic activity along subduction zones, shown here in black, or along a continental rift, here shown in red, were much more significant, much more important than they are today. So one important result of the game is that we have been able to extrapolate the present-day carbon dioxide fluxes to the geological past, just trying to compare the today's situation to a Mesozoic or early Cenozoic world in which volcanoes were much more active because subduction zones were more widespread and because continental rifting was much more important. And the result is this plot in which we have been able to quantify carbon dioxide emission through geological time. So time zero is today, so these are our current volcanic emissions, and as you can see, we can estimate much higher carbon emissions in the late Mesozoic to early Cenozoic, and these higher carbon emissions were responsible for higher CO2 concentrations in the late Mesozoic, in a warmer dinosaur planet. And we have also been able to quantify that the largest fraction of carbon on Earth is released by continental rift, here shown in red, while subduction zone volcanoes, shown in yellow, and middle ocean ridges, shown in blue, contribute much less gas than the others. So the message here is that the primary form of CO2 emissions on our planet is volcanism and tectonic degassing through continental rifts. So these are my conclusions, just to put together all the numbers. Here I'm trying to quantify what we have learned in the DECADE project. So in green numbers, we do know fairly well now. We know that the strong volcanic gas emitters on Earth release between 36 and 39 teragrams of carbon dioxide every year. We know much less about weekly volcanic gas sources, but our best estimate today is that these volcanoes release 15 teragrams of carbon dioxide per year, and by subtraction, you obtain that quiescent degassing is releasing every year between 51 and 53 teragrams of carbon every year. Eruptions are not very well known, but they are negligible on the long term because eruptions are not very frequent, they are sporadic, and so they contribute much less gas than quiescent degassing, while the most important form of carbon emission from volcanoes is likely to be diffuse degassing, which is unfortunately not very well known since so far. And to the right, our current best estimate for volcanic CO2 flux emissions on Earth. Tectonic CO2 fluxes are the big unknown. They are not very well constrained, but they are likely to represent the dominant mode of CO2 release from the Earth interior. So we are in need of a better estimate of tectonic CO2 emissions that currently have been set globally at 0.3, 0.4 gigatons per year. And by summation, we now know that the total volcanic plus tectonic CO2 flux is in the order of 0.5 gigatons of CO2 every year, a small number compared to what anthropogenic activities are currently releasing through human being activities. And I wish to thank you all for your kind attention. And if there is any question, I'd be happy to answer. Thank you.
Thanks, Sandro. So any questions or comments for Sandro? I have a question, Sandro.
Yes.
On the tectonic degassing.
Mm-hmm.
So when you estimated the tectonic degassing, how did you do it? Meaning that you took all the articles that measured in tectonic settings the emission, and how did you do the extrapolation? This is the question.
This is not my own work, but tectonic degassing was quantified in the study here. So what they have been doing is that they have used measured tectonic emissions that, as you know, are limited to very small regions of the world. They have calculated specific fluxes dividing by the areas, and they have then extrapolated these specific fluxes to the entire area of tectonic degassing on Earth. And so this number should be taken as an order of magnitude assessment. It is very inaccurate. The truth is that we need data. We need lots of data. We need a specific product on tectonic degassing because we need to quantify this flux in different regions, in different geodynamic contexts, in different geological contexts, and so on. Before we do this number is just to say that tectonic degassing is likely to be of the same order of magnitude or even larger than the volcanic flux.
Thanks, Sandro. Any other questions?
No questions.
No questions.
Okay.
So thank you, Sandro, for your nice presentation.
Oh, my pleasure.